Good morning, good afternoon, and good evening, everyone. Welcome to today's Ask the Expert webinar on surface contact and optical metrology. Our experts for today are Dr. Tyler Flanagan, our team leader, Dr. Ilya Herman, senior scientist, Dr. Byung Kim, scientist, and our moderator for today, Stephanie Williams, one of our other scientists. My name is Rena Samsu, and I am the senior marketing manager assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of pre-submitted questions for today's event, we unfortunately will not be able to get to all of them during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to one of our experts and moderator for today, Stephanie Williams. Stephanie?
Hi, thank you, Rena. So, hi everyone, thank you so much for being here today. So if we could get started on those slides, and we'll get right into it. So as you all know, you're here for the surface contact and optical metrology presentation for our three experts, and I'm going to introduce those three experts. So first we have Tyler. Tyler's our expert with optical profilometry. He has over 8 years of experience in nanomechanical and surface characterization, and he's been at EAG for about 2 years. We also have Ilya, who is our nanoindentation expert. He has over 20 years experience in materials instrumentation and characterization, and he's been at EAG for about 6 years. And we also have Byung, who will be our AFM expert for today. And he has over 15 years of experience in materials and devices characterizations, and he's been at EAG for about 1.5 years. I have also been at EAG for about 1.5 years, and I am a scientist in the XRD group. And like Rena mentioned, I will be the moderator and handling all of your questions and making sure that everything gets answered with our experts today. So now we're going to discuss a little bit about Eurofin's EAG after we get through our quick agenda. So we're going to discuss the smart chart, and then once we get through that, we're going to basically go through our three presentations, and then at the end, we'll have an additional Q&A. So Eurofins is a global leader in testing with more than 58,000 employees, 900 laboratories, and 54 countries. And Eurofins EAG is a division of Eurofins specializing in materials testing with over 45 years of experience. And we have more than 1,000 employees in 20 laboratory facilities all over the world. We have more than 2,500 different types of testing equipment and support over 5,000 clients. So what you're looking at now is our SMART chart. SMART stands for Spectroscopy, Microscopy, Analytical Resolution Tool, and it shows the techniques we have at EAG. The SMART chart allows us to compare the spot size and detection limit of each technique. So the techniques are color-coded according to the descriptions at the lower left. So blue is elemental information, orange is elemental and imaging information, the darker orange is chemical bonding, molecular structural information. And so within the box, you can select your technique based on the detection limit you need and the size of your area of interest. Then we have on the bottom of the chart, there is imaging techniques, and on the right of the chart, there are bulk techniques. So we also have another interesting infographic that's very helpful that that shows the depth of each analysis. And so we can see that AFM and optical profilometry are all the way on the left with a very shallow depth profile. And all the way on the right, we have nanoindentation. And with that, I'm going to actually hand it off to Byung, our AFM expert. Thank you.
Thank you, Stephanie, for the introduction. And it's nice to meet you all, and thank you for joining the talk today. I will show a dozen slides and spend next 12 minutes talking about the AFM instrument that I work with at EAG and what I do with it to help with the client project. So what is AFM? AFM's microscope that you can operate to observe topography. You can accomplish this by measuring atomic force interaction between tip and the surface. Here is a photo of AFM that we work with in our lab. You place sample on the stage and scan it with the tip to generate topographical image. You can load samples up to 200 millimeter in diameter and 15 millimeter in height. You can also work with a larger sample up to 300 millimeter diameter wafer, however, with overhang. The AFM has motorized stage and built-in optical scope, so you can navigate to desired visible location on sample, land on it with the tip, and do AFM imaging up to 90 micron aerial scans and measure features on surface as small as atomic step height to few micron for structures. In the center, you see schematic drawing of AFM setup that represents AFM operation. The AFM has 5 essential elements: cantilever tip, sample stage, XYZ actuator, light source, and light detector. First, the AFM tip is very sharp, typically has a 5 to 8 nanometer radius curvature tip and can be available at 1 to 2 nanometer tip. Next, the AFM tip is affixed to the XYZ actuator. The actuator is made of piezoelectric material, so you can move the tip with angstrom level motion control, precision, and accuracy in XYZ dimensions. Now, as for AFM operation, we load the sample, bring the tip to the surface, press it against the surface, and raster scan the tip X and Y direction over the sample surface. During scanning, the tip bends upward when it hits a bump, or it bends downward when it encounters a dip in the surface. To catch such depending motion, you shoot a focused light such as a laser to the top of the AFM tip. You then orient a position sensitive light detector to catch the light signal deflected off the tip as tip bending happens. The position where the deflect light falls on the photo detector relative to a reference point in the detector correlates to the height of the features on the surface. The feature height is then mapped out as a function of XY scan position on the surface to generate three-dimensional landscape information. On the left side of this slide is an AFM example, which displays three-dimensional topography of a static random access memory device. The tip bending motion of AFM tip contains mixed short and long-range force interaction signal between tip and surface. Using multiple filtering techniques, you can extract numerous interesting physical properties in addition to topography. You can, for instance, map surface potential to quantify work function among different materials. You can study ferroelectric properties in high dielectric gauge materials. You can characterize magnetic domain distribution in hard disk data storage. You can even check modulus and addition in copolymer rigid materials. Some of those imaging techniques that I just mentioned, you can use them to evaluate samples in air as well as in liquid. Furthermore, you can integrate different electrical sensors into the AFM to study other interesting electrical properties. For instance, including capacitance or resistance properties of samples such as in semiconducting films and devices. You can perform capacitance and resistance aerial mapping. You can do line profiling to inspect interfaces across multiple materials, or even perform IV or CV spectroscopy at a point of interest on the sample surface. Again, with AFM, you can investigate many physical properties in the same area you take the topography. You can do that with blanket samples or pattern device, which may available as received in planar form or prepared in cross-section geometry. In the following slides, I'll be introducing a few examples. I want to start with the surface topography analysis example because this is a type of AFM application used everywhere in all sectors of industry, from semiconductor to data storage to pharmaceuticals. This is also a type of application that no other analytical method but only AFM can accomplish. Example shown here is oxide film. We ran this sample in the air using AFM mode called soft tapping. is 1 micron by 1 micron area topography scan with 500 repeat measurements. The RMS surface roughness on the sample is about 2 atoms high, and the standard deviation is less than angstrom over 500 repeat scan. You can notice that the topography in the first scan and to the 205th and through the 500 scan are virtually identical. There is no change in surface or thus change in tip shape. Such ability to quantify roughness with angstrom precision, repeatability, and non-destructiveness to sample is a considerable advantage over other metrology techniques in research, development, and manufacturing. At EAG, we perform electrical AFM day-to-day for clients who send in all types of device, from CMOS transistor to photonic device, made on different wafers and with multiple materials, such to determine active carrier distribution as part of failure analysis and process development. This slide shows example using scanning capacitance analysis, a variant mode of AFM, to map doping distribution of silicon carbide power transistor. The topography on the far left is almost featureless, revealing nothing about transistor electrical properties. However, the 3 scanning capacity image on the right side of the topography acquired from same area in the device say otherwise and provide comprehensive electrical information. For example, the SCM amplitude data shown in the third figure from the left side of the slide provides information on doping levels. The phase image on the far right side includes information about the dopant type. The SCM combined data next to the topography displays the doping level and dopant type in one capacitance image. From the combined SCM data, one can imply that the thin, narrow yellowish areas labeled as the source are doped N-type with a relatively higher doping level than the large central area labeled N-epi layer. One can also gain additional details from inspecting scanning capacitance line profile drawn across multiple doped interface. From the phase profiling, you can notice the P-well to the N-epi phase transition occur over a short distance within tens of nanometers. However, the corresponding amplitude profile indicate that the doping level change is a more gradual process than what emerged in the dopant type phase transition. Nevertheless, from both profile shapes, one can tell that the N and P carrier amplitude annihilate each other and become neutral at the identical location where the N to P phase transitions occur. In short, the scanning capacitor data contains a wealth of doping distribution information, including carrier application, accumulation, depletion, and inversion around differently doped interfaces. It's a powerful failure analysis technique unrivaled by any other method spatial resolution-wise of mapping active charge carrier distribution. Here is a second example how you can use capacitance imaging technique to characterize doping distribution of different semiconductor device, in this case, SRAM device. On the left is doping distribution image overlaid on topography that shows NMOS and PMOS transistor with the P-type epi area residing in the central part of the device. The blue to yellowish represent doping levels ranging from 10 to the 17th, 10 to the 20th dopant concentration. The right side is the doping distribution line profile drawn across the dashed green line in the dopant distribution image. You can see a slight bump in the line shape, which corresponds to a 30 nanometer narrow region doped N-type to around 10 to the 17th of dopant concentration. Here, the question relates to whether you can do contact resistance measurement. The answer is yes, you can do that by using conductive AFM. In this example, a nanometer thick oxide was grown on a semiconductor and its topography and electrical current change with this bias between the tip and the sample was investigated. The left side shows topography. A bright boxed area in the center of the image is insulating region raised about nanometer relative to the surface outside. On the right side, a conductive AFM current image of the same area that display different current levels that flow in the sample with the various bias applied. The blue represent lower current flow. The yellow represent higher current flow. The boxed area corresponding to the insulator is highly resistive and remain unchanged in the current flow with increasing DC bias. On the other hand, in the semiconductor region outside the insulating boxed area, an increasingly higher current is passed between tip and sample with increasing tip bias voltage. Here is an example of electrical AFM, where you can evaluate contact potential difference between AFM probe and sample and use it to assess work function values which are unique to specific materials. In this example, one side of the sample is aluminum and the other side is gold. Aluminum and gold are the same height in the topography, but when you look at the contact potential difference map shown on the right side of the slide, the potential difference is significant between the two different materials. Considering that the theoretical value of the work function of aluminum is 4.3 eV and for gold is 5.1 eV, the surface potential difference over 0.84 measure correlates to the actual difference of both material work function nicely. On this slide, the question was related to sensitivity of magnetic force microscopy. In MFM, the AFM tip is coated with magnetic film and picks up the magnetic force from a magnetic sample surface. So like other example techniques that I have shown, you can get topography by default, and you also get magnetic domain maps simultaneously. On the left is the topography of a magnetic tape drive sample. In the middle is the MFM phase image. The yellow region and purple region correspond to magnetic domains opposing polarity. You can see a small circular bluish area in the MFM image. You take a line profile across it, and you can see its sensitivity is sufficient to resolve magnetic domain features that are 80 nanometer in diameter. Here, the question was about the AFM advantage over SEM. In all the AFM examples that I have shown, you get topography, a three-dimensional image in which you can quantify feature size in all dimensions in lateral and vertical directions. SEM, you are limited to 2D morphology, no quantifiable height information, and the analysis must be done in a vacuum. On the other hand, you can do AFM analysis in all environments, air, vacuum, and liquid. In addition, with AFM, you have more than 24 other modes. You can study various physical properties of samples, while SEM is limited to a few additional methods. The drawback as AFM is slower than SEM, and large and complex structure analysis can be challenging with AFM. This is the last slide on AFM. The question was, when do you switch to and from AFM and optical profiler? I will use optical profiler to do a large area survey scan and use AFM to do a zoom in scan. Optical profiler is substantially faster than AFM, so you can do surveys everywhere over large area wafer. And as much as you can do away with it, so long it allows spatial resolution. However, there are instances such as the surface topography waviness in the CMP process, or defects in wafer and device technologies that are too small below the optical resolution limit, so that only AFM can quantify the critical dimension accurately and non-destructively. This is where merging of both techniques for survey scan and zoom in scan, switching between two methods are suitable. With this, I wrap up the AFM part of the talk, and I will hand it over to my colleagues to continue with nanoindentation and then with the profilometry portion of today's presentation. Thank you.
Thank you, Bjorn, for the short introduction, and hello everybody to today's webinar. And I'm going to talk about nanoindentation in the next 10-12 minutes. And main question, what we need. So it's a technique which is on the smart chart located here in abscissa, probing 10 nanometers to about a millimeter range, and when it comes to nanoindentation, the main question is what can it be, what it can do for you. So what it does support, and the main answer is we're dealing with mechanical properties, and mechanical properties we need, for example, to understand failure modes, and for example, ceramic crowns, or wear in gears and machinery. Tribological applications, or if we design a thin film structure, we need to have mechanical properties, input parameters, or we have complex geometries where we also have need mechanical properties to predict its overall deformation behavior. So the general idea is we would like to design things which don't deform irreversibly, and and this is mechanical properties play a key role within this concept. So nanoindentation, how does it work was the question. How to measure the material properties such as Young's modulus from it, or what affects the consistency in the Young's modulus. So let's step for a moment to some basics here. All-in-one-far is a technique which is widely used, and there we record first the force displacement curve. So continuously recorded these two quantities, so we get a curve. And the goal is to link it to classical hardness testing, for example, where we measure a projected contact area with optical microscope, but in thin films, diffraction limits prevent us from doing so. So we get primarily information in depth. So to translate this in the contact area, we need to use models. So we use contact mechanics. So we describe first the unloading curve with a functional expression, and determine the contact stiffness as a derivative at the maximum load, and then calculate the elastic recovery, the rebound. So, and with this contact depth, we can go into a quantity which describes the relationship between the projected tip area and the distance from the apex. So this is obtained from a calibration. And then we can go with stiffness and the contact area into the Young's modulus calculation and then hardness calculation. Now, as a contact technique, we are deforming basically both sample and tip, and to deconvolute mechanical properties of the sample, we also need the mechanical properties of the tip, so Poisson's ratio and Young's modulus, to get a true Young's modulus. So now, when it comes to the main, what affects main consistency on the material, so even if you have a homogeneous isotropic material, your surface topography plays a significant role. So, such as if you probe laterally, we get side forces, and you can probe on the top of an asperity or in the valley. So all these will produce significant non-repeatability. Now, in order to kind of reduce the impact on the analysis, what can be done is, rule of thumb is penetrate at least 10 times the roughness of the surface. We can use indents or areas small enough so that the material surrounding looks semi-infinite to the probe or to the contact. Or we can also smoothen, of course, the sample. So we have dedicated teams to do so. Now, how a nanoindenter looks like typically, so we have a load frame, the gray part, we have an XYZ positioning stage, black, we have an actuator, which is either typically electrostatically or electromagnetically, also voice coil. So, and then we have the apparatus which measures the displacement, which is typically a 3-place capacitance sensor with a moving central plate. So we have some with multiple arrangement to measure in different dimensions the displacement. So our tools are from Bruker and KLA. And I mentioned already the displacement range, while the loading range ranges from nanonewton to newton. I mentioned already the so-called quasi-static approach, which uses contact mechanics, but we also can superimpose harmonic oscillation to the loading part, which makes it dynamic indentation, or the equivalent to DMA, which is called would be technically nano DMA. We also can do scratch analysis, wear testing, property mapping, thin film analysis, and box wear testing. The typical experiment starts by looking at the surface to identify suitable areas, clean of contamination and so on, and then shuttling over to the test location. And then on the task location, we also can use the same tip to profile or image the surface. The probes are interchangeable, and we're choosing shapes and sizes depending on application. We have to mount the samples. There are a wide range of techniques which are basically also up to the application, and we can do tests in various environments such as under pressure variations, fluid, temperature. Now, we discussed so what kind of quantitative measurements can be obtained from surface contact, general, what can else be obtained from indentation, what can the nanoindenter can do, where some questions along. And so beyond, so we call nanoindentation is a service line that we have, but it evolved into a kind of the more general mechanical testing covering imaging, tensor testing, tribal analysis, diction, compression testing, structure compliance, creep, stress relaxation, scratch, etc. So, and we can determine properties from that, such as Young's modulus and hardness, yield stress, fracture toughness, stiffness, and stress strain curves. On viscous material, we also can determine properties like creep, stress relaxation, storage, and loss modulus. And these are all indirectly obtained as we're going through modeling. But we also have quantities which can measure directly. So by just measuring a force, that's fundamental property which indenter outputs, for example, such as critical load for some particle compression or some coating failure, or the adhesion between the tip and the sample, also called stiction. No? So otherwise, other than that, we can characterize friction coefficient, topography, and coefficient of thermal expansion. Again, consistency on the material modulus, for example, was a question. And while it can be polished, the surface to make it, I mean, the ideal nanoindentation sample is shiny, and it needs to be polished. If it is not, we can take care of that. So the sample size can be up to 2 by 2 by 4 inch, and as a prismatic piece, but also in wafer form, it can handle up to 8-inch wafers, but which we cannot reach all the positions, but we can ensure that it doesn't need to be broken. On the small size end, we can handle samples up to 10 by 10 microns approximately, and we can test in invert, gas environment, vacuum, ambient conditions, liquid, and temperatures from 0 to 300 C. Now, a question was about what's the role of sample size on the material properties, the microstructure, and how can, for example, a tensile test compared with an indenter measurement. Now, in the tensile test, we have basically such a volume. The small constituents here, they kind of become negligible on the whole test, so it's averaged over a whole volume. In the nanoindentation, we are typically probe much smaller areas, and we technically can get between these constituents, within the white area and in the gray area within the area of interest. No? So we basically, depending on the contact area, we are measuring different properties, also called indentation size effect. Now, in order to get more comparable results, we can either theoretically could use a model to extract it or probe larger volumes by simply penetrating deeper. So this is what this one represents. Now let me go to some application examples. One was a question was about, can we do scratching on thin films? What is the preferred method to study adhesion? Is there a bond strength evaluation on a coupon for a film? And can we analyze adhesion between multi-layer films? So the answer is Scratch. Scratch is a very nice tool because it doesn't require any sample prep, and it is very repeatable, and it's relatively easy to apply. So what's typically done is we perform a tilt-corrected multi-pass scratch. So typically the first pass is profiling, longitudinal, And then we take these two-bit topography in account to calculate the loading profile, apply it, ramp the load. While we do this, we measure the normal displacement, and thereafter we do another longitudinal pass, like indicated here, this dashed line, and we can do perpendicular passes to look at the profile. So we can get a range of properties such as information about the pile up, which gives us about information about plastic zone and the moment of failure longitudinally, and also where it fails depending on the step size in this profile thereafter. Then we had questions about, can we evaluate the hardness of multilayer films or buried films, how we can measure precipitates or inclusions, and is NI useful to measure hardness of grains? Now, this isn't working well in top-down, so there would be too many assumptions involved. So the way to go would be a cross-section technique, and we have different ways to produce them. In general, we basically we produce samples either 90-degree cross section through a coating stock or slanted. So the result is basically a rectangular area of interest, which then we analyze by a form of mapping. So to illustrate this, I am having here a heterogeneous material, which can be, it's not a layered material, but it's a multi-phase material. It's silicon particles in aluminum, and you can see nicely the how in the false color image the contrast in the properties. So the harder particles in the soft matrix, and we basically get a histogram which we can analyze statistically to extract constituent properties, and so we can do with individual layers. Now, the question was, can we measure the internal stress within glass? So the answer is nanoindentation is not a good way to do it quantitatively, but fracture toughness testing is very sensitive to residual stress in the coating. So to give you an idea how it works, so fracture toughness measure, we need a hardness in the modulus, of course, to calculate that, and then we produce a series of indents with increasing loads until we have cracks emanating on all corners. So with the crack length in the modulus and hardness, we can go into fracture mechanics in order to get a fracture toughness. Now, this result is valid, of course, for homogeneous isotropic and stress-free materials. So depending on whether we have compressive stress or tensile stress in the material, we have shorter or longer cracks. And if we have a reference, let's say an unstressed material, that's a very sensitive way to evaluate at least whether the sign of the stress. Now let me come, this will be the last application, and it was about the minimum coating thickness required for nanoindentation to get accurate results, the coating properties, and how to deal with substrate effects. So here's an example where is the depth gradient for the hardness and the modulus. What you can see, the hardness starts lower, increases, and similar for the modulus. So this is a soft material, soft coating on a hard substrate. And in order to get the pure film properties, there are going three ways. One is we use that we basically get the values and average at 10% of the coating thickness, and the plateau method, which basically looks at where these properties saturate. For example, here it's up to 30 nanometers. We would take an average, and sorry. Okay. Yeah, that was basically the last slide, and I'm handing over now to Tyler, talking about profilometry.
Thanks, Celia. Give me 1 second. Press these slides. Okay. So yeah, I'm going to be talking about optical and stylus profilometry today. There we go. Back to our smart chart. OP and stylus is pretty much a surface level technique. Stylus definitely surface level, and then optical profilometry, you can sometimes measure film thickness, which I'll cover later in the talk, so down to a couple microns. So starting off with OP here at EAG, we have a Contour GTX8 from Brooker, and it's good for measuring topographical information, metrology, so critical dimensions, width, height, pitch, surface roughness in areas from 50 microns up to 70 millimeters squared with stitching. And it can go from a height range of about 0.1 nanometers up to 10 millimeters. And down there I have some lateral resolution for our most common. The vertical scan is about 1 nanometer Z resolution with about 500 nanometers in the X and Y. And then with something called phase shift, we can get down to about 0.2 nanometers to 200 nanometers in the XY. So what is optical metrology? There's several different types. I'm just going to be covering optical profilometry in this one, but there's ellipsometry, all this other stuff. But so basic way an optical profile works is you have a light source, which goes into a beam splitter. So you create two light paths, one of which goes to the sample and one to a reference mirror. They bounce off and come back, and then they reconverge and go to the detector. And when their path lengths are approximately similar, an interference pattern will occur, and it uses this to measure the intensity to determine the height. And there's two modes, vertical scan and phase shift, which couple vertical scan right here. We had a question, what are the differences? So with vertical scan, the optical turret actually moves up and down during the test. You can see here, this would be what a step height would look like at your first focus level, and then at your second focus level lower, and you can see you have this fringe pattern. And so as the turret moves up and down, it'll move these two frames in and out of focus, and it can measure the height differences between these two. So key applications for vertical scanning, right here I have a key head, and so people are asking what are the best applications. And so here we have the 2D and 3D image that you would generate from this. You can measure the roughness value of the sample, and then you can also look at the critical dimensions. And vertical scan's really good for rougher samples or samples that have a lot of variance in the height and critical dimensions. Now, phase shift, in this case, the reference mirror itself is moved in fractions of a wavelength by piezoelectrics. And the intensity at 90 degrees of the phase shift is measured, and it uses this information to calculate the height. This is better for very smooth surfaces, so think like a silicon wafer or thin metallic films. And the height resolution is a lot better for this technique, but it doesn't really work for materials that have, several microns or, hundreds of nanometers in the height difference all that well. So someone asked how to get the closest results from optical methods in AFM, which is a good point, good question to ask. And so also, what is the smoothest surface roughness we can measure? Here I have a silicon wafer, and here's the roughness values. You see it's sub-nanometer. And comparing the resolutions of the two, AFM still has slightly better Z resolution. You can get your noise floor down to tens of picometers, where it's a little bit higher here, and you can get XY resolution down to about 10 nanometers, really determined by your nominal tip radius. Whereas OP, we're limited by light, right? So in the XY, so we can get a Z resolution of almost to an AFM down to about 0.1 nanometers, but the lateral resolution is always going to be significantly worse. Someone asked about bearing structures, and so I figured I'd cover film thickness here. And so the question is, can you accurately measure defects at interfaces buried with multi-layered coating constructions? And the answer is, it's really hard. So basically, here I have what would fringe pattern would look like on a thin film that's over a couple microns. And you can see that you have these two envelopes for the interference patterns. And so these are fairly easy to deconvolute. So as long as you know the refractive index of your coating on what we call thick samples, which would be greater than 2 micron thickness, it's more trivial measurement, but once you get below this thickness, those envelopes can overlap, and it can be much more difficult to deconvolute the two. You know, you need a reference material of a known thickness of the same type, and you need some modeling to really figure it out. We had another question about common artifacts and data processing, and so I threw the two most basic ones in here. And this would be missing data. So with optical profilometry, it has difficult getting measurements or data from highly curved or lateral surfaces. So you can see here, this is just like a standard sample we have to do our calibrations. And you see all these dead pixels on the left here at the edges of these bars. And so the software has data interpolation called data restore. And so that's one way to process that. And then oftentimes you have to tilt the turret, or your sample's not totally flat when you're measuring it. So you'll have artificial tilt, and then you can just use plane fitting for that. There's other optical artifacts you can get, like and really smooth curved samples. You can get sort of leftover from the interference pattern. You can remove that with like Gaussian filters, stuff like that. Moving on to stylus profilometry, we have a DECTAC XT, also from Brooker. Again, it's good for the measurement of topographies, metrology, critical dimensions. It can take measurements at lines up to 55 millimeters and has a height range of up to 1 millimeter. And the resolution is somewhat comparable with OP. It's about 1 nanometer in the Z, and then the XY is determined by your tip radius, which we have one that goes down to about 200 nanometers or 500 there. So one question, in which case is stylus better than optical profilometry? So going back to those film thickness measurements, let's say you just want to measure the top surface roughness. It's oftentimes a lot easier to just do stylus measurements on those things, especially if they're curved surfaces. Because if you don't have a flat film or a flat substrate, then it becomes a lot trickier to deconvolute the two envelopes or the two fringe patterns. So on samples like that, I would usually just go with a stylus profilometer. Then we had questions about material compliance for stylus profilometry. So when you're taking stylus profilometry measurements, the hardness can have an effect. Typically, no, but when you get down to like really soft materials in the kilopascal to single-digit megapascal range, you can, it enacts force on the sample. And that can cause localized deformation while you're measuring it, totally skew your results. So materials like elastomers, organic films, oftentimes you can't do stylus. And just to wrap it up, these two techniques are fast and typically non-destructive. You can cover large areas, especially compared to like atomic force microscopy. And then the limitations, again, missing data from rough angled surfaces, curved samples can be tricky, and you can get some optical artifacts in the case of optical profilometry. So our Q&A session.
Okay, so please feel free to keep putting questions into the Q&A section, but we're going to get right into this. So first, I have a question for Ilya. So this was brought up when you were on slide 25. It said, what is a technique that can be used for measuring the film adhesion to the substrate?
So to measure the adhesion to a substrate, it depends on what type of adhesion you are looking for. If you would like to put it into a finite element calculation, you would be needing an adhesion energy, for example, or if you would like to compare one process against the other. So the practical adhesion test, like I presented already, would be appropriate. And the practical adhesion test is, as I said already, it's a lot simpler to prepare from the sample preparation point of view.
Great, thank you. And this was a question that was brought up while Tyler was presenting, but if this is not a optical profilometry answer, then feel free to chime in. It says, which method is the best to measure microcracks on polymer thin films after a fatigue test?
So you definitely use profilometry to measure that, either optical or stylus. Ilya covered fracture toughness. Unless you're doing like really small cracks, then sometimes you'll need atomic force microscopy. But in general, you can get it done with profilometry.
Great. And we have a question for Byung. Can domain walls in ferroelectric thin films be imaged with AFM?
Yes, using with piezo response force microscopy, it comes with you gain three information with that technique. First of all, you get a roughness and morphology information, but there is something called amplitude data, just like in many of the other techniques, that will provide the domain wall contrast between different domains, and then it also comes with phase information. It will be able to tell you whether the domains have polarization that are directed in different orientation. So answer is yes. We can do that with the technique called the piezo response force microscopy. As long as, depending on type of materials, you could apply various different techniques. A lot of, you can probably apply capacitance, be able to see some of the contrast, along with a few other techniques.
Great, thank you. And Tyler, for optical profilometry, I noticed that after aligning the turret tip tilt against the sample, a single scan would show up as flat, even without the tilt plane removal. But a stitched montage would show up as tilted. Is that typical?
It's interesting. I'm not entirely sure what would cause that. I know sometimes if the calibration isn't totally right, the stitching, you can end up with checkerboarding. It could just be that you're covering a large enough area where, in the single image, the tilt isn't as obvious, so that as you go further along, you could be seeing it more. But I'd have to look at the data to really answer that one.
Okay, and then for this one, how do you measure and map the VIA openings that are 100 micron deep? This could be a other technique as well.
I'm not sure what VIA means, so I'll have to get
We can move to another question. Can the optical, I should say, how do you measure accuracy, or how accurate is optical profilometry? Because if a profilometer is not able to go deep enough.
So, I mean, your total range, right? Like with an optical profilometer, you're limited to 10 millimeters. If the opening's more narrow, you might not be able to get data from the bottom, but it really depends on the sample geometries. In terms of accuracy, machine internally calibrates, but we do SBC tests every week, get yearly calibrations, and the plus minus is about 3%. It gets a little worse once you get into like phase shift and really smooth samples, but it's a very accurate technique.
Okay. And Ilya, we have a question. How do you characterize the material properties such as the Young's modulus, and will AFM results correlate with bulk material tests?
So first of all, I wouldn't, when we talk about Young's modulus, AFM is not ideal and the ideal technique. So it would be more like nanoindentation. But we use contact mechanics, and our AFMs there can also apply force displacement curves, and which we can model and extract the Young's modulus. The metrology chain is just much longer with an AFM. So if you're really the question, the real question is whether we need the resolution, the lateral resolution of an AFM in order to get the mechanical properties, or if your sample or grain size are large enough, we could be using already nanoindentation. because we have some overlap between nanoindentation and AFM in terms of spatial resolution. So yeah, hope this answers your question.
Okay, this one might go out to all three of you in terms of, you know, the scale of the analyses, but what are the differences in results? What differences in results would you expect between nano hardness and micro hardness?
So let me take this question. So but there are clear definitions on nanoindentation. The nanoindentation per definition goes anything shallower than 200 nanometers. That's based on the IC 50577. So anything above is then microindentation. So it really depends on how the data were collected earlier, and but generally the contact mechanics is the same for both. So it really comes down to what I showed earlier. The slide is the microstructure. How does the microstructure compares to the contact size? So if it's comparable, well, yes, you can compare them. If you probe with a nano indenter between the constituents and the micro indenter averages over 10 of them, no, then they are not comparable. So it's an indentation size effect clearly.
Okay, great. And Byung, do you have PFM, piezoelectric force microscopy application? Do you have an application example for PFM?
I don't have it with me to show you today, but we do, first of all, we do offer the PFM, as I just mentioned to you, PFM imaging as well as spectroscopy. Just give a quick in PFM is, piezo materials essentially mechanically expand or contract when you apply electric field, and something from the data that PFM phase, you can evaluate sample, which direction the piezoelectricity is pulled, either in one direction versus the other. And you can also judge how much piezoelectric displacement occurred by looking at the data, the amplitude signal that comes with the PFM technique. You perform spectroscopy to assess, for example, threshold values in which the piezoelectricity switching takes place from one to the other piezo polling states. And you can also assess strengths of piezoelectric domains and the shape of the resting polarization state in the piezoelectric materials. So again, we do offer, but today not able to provide actual data.
Great.
Hope that gives you some answer.
Ilya, what is the benefit of nanoindentation compared to normal DMA, dynamic mechanical analysis, for mechanical properties measurements?
So nanoindentation versus DMA. So there is let me put it this way. Results are closely comparable to classical mechanical testing, like uniaxial tensile testing. So this is simply because we are using contact mechanics and continuum mechanics. So the physics is different. In DMA, we are using the damped harmonic oscillator physics. So it's a completely different Newtonian equation where we start to model from. And for non-visc, so materials with no strain rate sensitivity, results are surprisingly, not surprisingly, they are actually quite well comparable with each other. If you have materials like polymers, soft polymers, and in certain frequency ranges, so a nanoindentation typically ranges from millihertz to hertz. That's the strain rate range, and DMA would be covering, our DMA would covering from hertz to several hundred hertz. So there are, if you have a material, a kind of silicones also, the results are expected to be different in certain and at low frequencies, for example. So there are, and if you would like, but for better comparison, with classical techniques, the nanoindentation is better. While it's not ideal, while you would not want to use that at all for very soft material, for example, you have to do DMA or nano DMA.
Okay, and Byung, can you image crystal lattice planes with AFM?
Well, let me give an example, we can first of all imagine something called Mori superlattice structure, such as in the sample like graphene monolayers deposited on boron nitride stack core crystal planes. We can imagine this lattice structure down to few nanometer periodicity. From those spacing, you can measure and determine the twist angle between two different planes, crystal planes. You can also, analyze the electrical and mechanical property using AFM of such nanoscale superlattice patterns, such as using conductive AFM, capacitance imaging, as well as surface potential techniques that I have presented today.
Okay, and can we quantify residual stress with nanoindentation, or is it more of a comparable experiment?
So yeah, there was one slide I addressed this a little bit. There is no direct way, no easy way, but it was of course demonstrated that it is possible. So the idea is nanoindentation itself introduces residual stress. So we create a plastic zone, and it is confined by an elastic field. Now, if we have, so this allows us to measure the hardness. Now, if you have an external residual stress superimposed to the elastic field, and the amount of residual stress is comparable to the yield stress of the material, then we will get measurable influence on the raw load displacement curve. So they get deeper or shallow. And with a reference material with a known stress state, we could basically extract the residual stress, so in reverse. But it's unfortunately hard to do, for example, in ceramic materials. It may work in metals, but not in ceramics.
Right, and so Byung, how would you characterize the surface texture of soft and fibrous materials?
Yeah, you can evaluate the texture of different size fibers, such as in Kevlar, and then the human hair, collagen, or carbon nanotube, even down to DNA strands, right? But what you need is you need to immobilize them to do AFM texture analysis, such as on a flat substrate like glass slide or mica, HOPG substrate. Then once they are immobilized, you can take a look at them in air or even in liquid, if you can hold them detached from the substrate surface. You probably, for the soft fibers like DNA or collagen, for example, in liquid condition, you would probably need to use soft tapping or peak force type mode of AFM analysis.
Okay, and I'm going to open this up and anyone feel free to answer this question. Can the local dielectric constant be measured using scanning capacitance?
Absolute quantification, I think, is challenging. Scanning capacitance will give you capacitance image along with, as I presented, the dopant distribution and the dopant types. We'll probably trace back to approximate, those capacitance values using, capacitor. We have two different techniques, something called SCM and the scanning microwave. But I would think absolute quantification, I think, is challenging.
And with that, I'm going to ask our last question. Actually, we have one or two more questions. What effect does humidity play in the collection of AFM data?
So can I take that?
Yeah, go ahead.
So basically, what happens? You have there's the fluid in the atmosphere, in the surrounding atmosphere, gets between the probe and the surface, And if you don't take in account these adhesion forces between these two solids, you will basically falsify the results. So generally, with AFM, you have to take in account these adhesion forces in order to get any accurate results. In
Great. And
nanoindentation,
then go ahead, finish.
we can measure this with nanoindentation as well. It's just we can apply higher loads as well, so that it becomes negligible to some extent.
Okay, great. And then we'll finish it on one last question. Could nanoindentation be used to quantify the thickness of a soft polymeric coating on the surface of a polymeric substrate?
Well, it could be done indirectly. It's not the ideal method to do so, but the idea is the following. We can, for example, wear the sample through. So it's like it's a wear test, scanning wear test. We could do multiple cycles, and we have means to detect, for example, the material properties while we go into, and depending on how deep we have to go, well, to the interface, that's going to be our thickness. We also could do a scratch test and basically measure the step height with the scratch process I illustrated earlier. So these are estimates, of course, they are much more accurate ones, but it's a result we could get along.
Great. So today we're going to summarize and say, well, why would you choose Eurofins EAG laboratories for your analyses? And what, you can read all the bullet points on the slide, but really the one to emphasize is the first bullet point, which is client confidentiality is core to our business. And it's something that we take very seriously. So with that, I just wanted to thank everyone for coming, and then Rena, take it away.
Thank you, Stephanie. Just wanted to say thank you again to all of our experts and for this robust discussion and presentation. And thank you to everyone for attending today's event. If we didn't get to your questions today, we'll be following up with you soon. And if you have any other questions, please send in your questions to the email address on the screen. That's customerservice@eurofinseag.com. Also want to mention that I've added a few links to our resources in the chat window, including next week's webinar on corrosion testing for medical devices. So please check that out. And once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. So on behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today, and have a great rest of your day.